Very much for the opportunity to present at this meeting. I had a very good time. I learned a lot this couple of days. So I thought I would tell you about an effort that we have been focused on for the past couple of years. This is in collaboration with my student Bernardo Finelli and postdocs Lucas Antoni, who will soon move to Columbia, and Garrett Goon, who's coming to Cambridge with me. So, and this is about cosmological aspects of a shift symmetry. So the main message of the talk will be I'm going to discuss how you go in general from symmetries to cosmological observables. Some of the techniques I will be using are common and well known in field theory, and perhaps surprisingly they had not been used for the symmetries I'm going to discuss here. And I'll discuss how to do this in two different ways. One is by defining an effective field theory with respect to symmetries and computing stuff, and the other is by deriving non-perturbative soft theorems. And the worked example that I'm going to focus on of symmetries is one particular symmetry, which will be the shift symmetry. So in the rest of the talk, I'm going to spend 10 minutes to argue why the shift symmetry. It has been mentioned probably 150 times already, so maybe it doesn't need that much motivation, but that's kind of what I'm going to study. And at the end of the talk, perhaps the punchline, if you want to go home with one thought, is that theories that are natural in the top-down sense and shift-symmetric, they have very distinct prediction, and they give you non-Gaussianity of a very specific form. This is the FNL equilateral and orthogonal plane, and shift-symmetric theory can only give you prediction within this line if they are natural. So that's what I'm going to try to convince you of. OK, motivations. So how do we go from symmetries to observable? And I'll discuss the shift symmetry. In particular, the question that I want to ask is that if I hand you a set of cosmological correlators, all of them, and I ask you, was this theory shift symmetric or not, I want to answer that question. Is the answer yes or no? I don't want to be discussing whether the anything else except for cosmological observables. So this should be something that we should be able to determine. This is what we do in particle physics. If I give you the amplitudes, then you can tell me which symmetries are realized in the amplitude and which not. So we should do the same in cosmology. And it is a little bit surprising that despite the fact that shift symmetry is so used in model building pretty much everywhere, it wasn't completely clear what the consequences are for the cosmological correlators. So the motivation one has been mentioned a few times, and Liam did a great job reviewing the motivations for the fact that inflation is a UV sensitive mechanism, and then if you allowed generic operators that you expect to couple to your inflaton when you UV complete the theory, they can change the prediction of the theory unless the theory, the model you were working with, has particular construction or certain symmetries that made it robust to generic UV completions. And so this is the classic example of dimension 6 Planck-Sachs operators that give you corrections to Ita's law roll of order 1. There is another meaning of naturalness, which is the bottom-up meaning. That's often what we use in particle physics. It means a theory or a field theory to be radiatively stable under its own corrections. That's a weaker conditions. Here we are trying to impose something stronger, and it should be stable under coupling to generic Planck scale physics. And so you should have a good answer for why these operators do not completely spoil what you're trying to do. And the shift symmetry is a known useful device to control both perturbative corrections generated by the theory itself, as well as coupling to some UV complete theory, and they have been used in pretty much model building in field theory and string theory for a couple of decades, or maybe even longer. Perhaps another reason why I was interested in discussing shift symmetry is because of the role it plays in many of the conjectures of what might be the constraint of quantum gravity on low energy effective field theories. And it would be interesting if we could determine observationally whether or not a shift symmetry is at play in the early universe. Rather than arguing if it is a useful device in model building, maybe we just as an observable that gives us a yes or no test for whether the shift symmetry is at play or not. And perhaps more on the formal side, if you have been interested in this discussion of super Planckian, whether super Planckian inflaton displacement are allowed or not in a theory of quantum gravity, I do not believe that talking about field displacement is the correct language. I think there are explicit counterexamples, but perhaps it is interesting to try to nevertheless express certain constraint on the low energy effective theories, but in terms of constraints on the correlator, something that one can actually measure, rather than some perhaps abstract notion of geodesics in some field space. Yes?
So will you define shift-symmetry, like the fact that epsilon 8 or small is the shift-symmetry or not?
No, but this is my definition of shift symmetry, and the consequences for inflation, I'm going to discuss them now in the talk. So I'm going to start from here, see where I get, and I'm going to show you that in general, they are not as simple as epsilon eta being small.
Exact symmetry, not
exact symmetry, yes.
Of order broken by order slower parameter.
Yeah, great question. So the first 20 minutes of my talk will be exact symmetry, no breaking, and the last 10 minutes approximate shift symmetry, in which I allow for a control breaking. So we will get both parts of the story. So if it is unclear whether it's exactly broken or not, please ask me again. So the first 20 minutes is exact. So continuous. I was trying to buy myself time, but Matthias was paying too much attention. Okay, so at the beginning. The third reason that I'm maybe going to skip is that lambda CDM is well approximated by a shift-symmetric scalar field theory today, right now. So maybe our future is controlled. I can discuss this. It's a detail. Okay, so approach number one, effective field theory. There is already a long time ago, Leonardo and Paolo and collaborators told us how we should think in a model-independent way about inflation by looking at perturbations, and by fixing a gauge to be co-moving. We can say that the most generic single clock model of inflation is described by an action which is invariant under spatial diff, but no time diffs. So I can write stuff like G00 and time explicitly. If I expand this in perturbations, I get, well, infinitely many operators in terms of delta G00 or extrinsic curvature with arbitrary time-dependent coefficients in front. Sometimes it is useful to rewrite this theory in the decoupling limit, in which the Goldstone boson of time translation decouples from the metric, and this is the form of the theory. And again, we see this infinitely many time-dependent function. Now they become function of the Goldstone itself, and so there are infinitely many operators that you have to choose to specify what theory you're looking at. And just to stress, even though this is always called the effective field theory of inflation, of course, there's nothing to do with inflation. It's just an effective field theory of any cosmological background. So there is a little bit of a standard lore that having a shift symmetry in whatever inflaton you have might tell you something about the time dependence of these coefficients and of these other coefficients. In particular, in some cases, one might make the simplistic assumption that these time-dependent coefficients are constant when there is a shift symmetry. That connection is not true in general, and the real connection is what I'm going to try to work out. So it's not true that if the theory is shift-symmetric, this function is constant. The simplest possible example is like take really the most shift-symmetric theory you can think of and make it free, and let it evolve cosmologically. We know that the solution of this is phi dot is 1 over a cube, and so the coefficients in this theory are everything but constant. They're going to be evolving very, very fast. And so an exact shift-symmetric theory definitely does not have constant coefficient. This was pointed out by Nicolis and Piazza a while ago. So let's see what the actual constraint is. Okay, so just to define the shift symmetry again, now we have a theory in which there is some inflaton and the metric. The theory is diff invariant, so they both transform under Lie derivative with respect to the diffeomorphism parameter, and the shift transforms the inflaton, but not the metric, which is invariant under shift. So typically when we work in the EFT of inflation, which is what we're going to try to do, it's convenient to fix the diffeomorphism in such a way that the inflaton is unperturbed. In the generic case, this kills all possible time diffs, because I need to use a time diff to fix the gauge. But if the theory is shift symmetric, there is one single time diff that survives this gauge fixing, and it is given by this particular one. If I do a time diff in which time is shifted by c over phi dot bar, whatever phi dot is, it can be an arbitrary function, that transformation does change this gauge condition, but only by a constant, which is a symmetry of the theory nevertheless. And so that transformation is yet a symmetry of the theory. So if we want to write down the most generic EFT of a shift-symmetric cosmology rather than a general EFT of cosmology, we should again write down the most generic theory like before, but we have one more transformation, this time-diff that we have to apply. So I'm going to take the EFT of inflation as we had it before, which is this one, and I'm going to impose that this one is invariant under this one time diffeomorphism. Yes.
Big phi is the same as little phi.
Yes, you're right. Yes. Yeah, sorry for exchanging.
It even appear in the EFT?
It doesn't appear. It's a parameter that defines your symmetry. So
Like if I want to impose this condition.
yes.
Maybe I see the index.
Yes, it's the next slide. Yes. Here you see where it appears. So this is the action. We know how the metric transforms under this particular diff, because it's just a diff, so it transforms like this. So the transformation is one particular time diff that depends on the function phi bar time. So you give me some phi of t, and there is one particular time diff that the theory should be invariant under. So in some sense, there are, yes. And if you take this one, shove it into the Lagrangian, and ask that it changes only by a total derivative, you get a constraint for the time dependence. And just to write it down to lowest order, in which we just only do delta g to the n without any extrinsic curvature, just the simplest one, the relation is given by this formula. So the n plus 1 coefficient of delta g 0, 0 to the n is related to the n coefficient and its time derivative.
Does it also put a constraint on the leading terms, the tadpole terms, or now they are not included?
Yes, they do, but yes, yeah, it does. Then the next slide, you will see that there is an interesting constraint. So this one, in some sense, it's a constraint that you can interpret as a constraint on the equation of motion. I'll show you in the next slide. Yes.
In the limit in which phi bar dot becomes a constant.
Yes. Yeah, I hate that we write it that way, but the real equation is everything multiplied with that coefficient with the 2. Actually, you should multiply the whole equation by this quantity. I divided by that. But if phi bar dot is constant, what the equation tells you, as you exactly said, is this, which is the standard law. So if you indeed can have a linear in time evolution, it is true that all the coefficients have to be constant. But in general, these theories don't have only linear in time evolutions. So if you want to have just for people that maybe don't think about the EFT day and night, a Lagrangian, the covariant formulation of the theory I'm talking about is P of x, where x is d mu phi, maybe with a minus. And in flat space, these theories have always linear in time solutions, but when you couple them to gravity, no. And so this is the most generic case. In particular, that, for example, is a simple example where phi dot is 1 over a cube. OK, so this is the implication of a shift symmetry. Some remarks. It's pretty cool that adding one symmetry has fixed all infinitely many time-dependent functions to leading order in derivatives. So before we have d1, d2, d3, d infinity. They were all time-dependent, unknown. And now they're all fixed, because you can start solving this one from n equals 0, n equals 1, and they're all fixed in terms of d1. So shift-symmetric cosmology, if you tell me what the background does, h of t, the whole theory is fixed to lowest order in derivative, all interactions. Remarks number 2 is that you can do this with all the extrinsic curvature, and you can put delta R3 and whatever other operators in the EFT, and they're all fixed, and you can go through the calculation. It's some similar formula, but I didn't want to discuss it. The other remark is that maybe more to what, Merdad, you were asking. Let's look at the lowest, what this tells us about the background. So we take those relations that I've written there, just so that you guys remember, roughly speaking, what the relations look like is dn plus 1 is over the dn plus dn dot. So if we take that expression for n equals 0, 1, and 2, and we play with them, we get this equation. So far, this was valid for any FLRW. So if you want to do inflation, so close to the sitter, you want epsilon and eta small, but you see it's impossible because this is not 0, so you can take it out. And this expression has a 3, and then epsilon and eta. So epsilon and eta cannot be both small. So there is no slow roll inflation in this theory, which is kind of a nice consequence of symmetries from this point of view. So it does constrain the background, as you were asking. OK, there is also an alternative formulation of all of this in clock time, in which the evolution becomes linear. But if the evolution is, you can always do a time diff such that the evolution is linear. But when you do that, you cannot write this coefficient anymore as being a 1, because you usually use time diff to do this. So if you undo this, here you would get some arbitrary function of time. And so, OK, so then the derivation is. I'm going to have to make it approximate and break it a little bit to get something observable, sadly. I was hoping that this would have been, but if the shift symmetry is exact, then there is no slow inflation. So I have to make it approximate, hence the last 5 minutes of my talk. This theory does give you something interesting, which is this. Well, interesting. It gives you ultra-slow roll. So you can do ultra-slow roll inflation, for which eta is -6. So it's very far from slow roll. But as you know, you still get an s minus 1, which is small because of the decaying mode of zeta now becomes growing. Ben? So you're forbidding a purely linear? All potentials. Yes. But when you couple it to gravity, no. So we also do the non-gravitation description, in which we allow the linear term. And we describe this, what we call driven superfluids and imperfect superfluids. And there is an interesting story. But yeah, I didn't have the time to discuss it. But when you couple it to gravity, that transforms into square root of g, which is not a constant. So. I'm going to discuss the breaking at the end of the talk. So when I go through those slides, maybe you can ask me again if it is clear what I mean by breaking. So far, I'm not breaking it. So I don't want to jump there yet. Yes? Your potential is exactly flat? Now it's exactly constant. Yeah, but p is an arbitrary function of x, which wasn't obvious to me that this didn't inflate. But OK, maybe some people knew it. I didn't. I hadn't found it in the literature. Because p of x is a complicated function. In fact, we know that there is the Gauss condensate that is almost the sitter. But what this tells you is that no matter how you approach the Gauss condensate, eta is always large when you approach it. So you approach the sitter fast.
The sitter is exactly flat, and you say that it doesn't inflate?
It's not slow roll inflation. By slow roll, I mean eta has to be.
Slow roll. If you roll the field along the sitter flat potential, it will certainly slow roll.
No, it's not, because
No, of course it is.
eta is -6. But I'm happy to discuss with eta is -6 constant in that case. It's this model here. So it's not slow roll.
If you solve equation for the scale field sliding on the top of flat potential, then at some moment the velocity becomes small, and then it is small slow roll, etc.
This is not.
H dot is small, right? That's an H double dot. That's what we care about. So.
This is the definition of eta that I have, and it's -6 in this model. I'm not doing anything. I'm not trying to trick anyone. Is this the definition of eta that we use? It's -6 in this model here.
What I was trying to say, that the solution, when you have the sitter potential, and you put the scale field, minimal kinetic terms, no things about CS, etc., solve exactly the solution of motion over the scale field, it just slows down.
It does.
And at
Like
some moment,
1/8 to the 6.
and at some moment, its velocity becomes nearly 0.
Nearly 0, yes.
Okay, so what's the problem?
It H dot is super tiny. Epsilon goes like 1 over a cube, which is equal e to the minus 3n number of e-foldings. And yet, eta is minus 6. It's not slow roll inflation.
Another thing that it will not give you.
It's a semantic.
Okay, maybe it's semantics. That is what people call ultra slow roll inflation, and eta is very large. But okay, I'm happy to write down, and we can.
It's a bad model, but what I told you about, it's a bad model. It doesn't fit experimental data.
Okay. Yeah. Okay. So yes.
The exact Goldstone you said is not an example in which you have exactly the seed.
Yes, by slow roll inflation, I want epsilon and eta to be small but not 0.
In the equation, you are assuming that they are not zero.
Yes. So I'm trying to actually get inflation eventually. As Matthias said, no, I'm not yet there, but I'm trying to get there. Okay, so I'm going to discuss quickly the soft theorems because I think that the techniques that we use were quite interesting. And they have to do with adiabatic perturbations, which, of course, in PDF are not going to show as cool. So this fruit doesn't make any sense to you. Okay, so let me skip that. I thought I had a video, but I didn't. Okay, now this is a PDF. So that doesn't make sense. Okay, so the universe is like a pile of fruit, but it's the same pile of fruit everywhere, with the fruit being a little bit bigger or a little bit smaller. And that's what we call adiabatic perturbation. So delta rho over rho dot over rho plus p for every component of our universe on large scales is the same. That's perhaps one of the most remarkable facts about our universe, and perhaps is the legacy of our generations to explain why this is the case. We have one explanation, which is a single field inflation plus Weinberg argument. Weinberg noticed that there is a generic set of solutions of GR, or in fact of any diffeomorphism invariant theory, that are built by doing fixing the small gauge, performing a diff. Since the theory is diff invariant, that's again a solution. It's just the same solution as you had before in different coordinates. But some of those diff extend to finite momentum. And those that extend to finite momentum, they become physical perturbation, for which you already know that they are a solution because you just checked it. This is a clever way of generating new solutions, but what's very interesting is that the solution we consider, for example, in single clock cosmologies, are exactly of that type. They are locally indistinguishable from a diffeomorphism, and so are the tensor modes that we consider. So just to set the notation, what I'm going to call adiabatic modes for the rest of the talk are physical perturbations that in principle I can measure, but they're locally indistinguishable from a change of coordinates. So you need to make more of a non-local measurement, so wait some time or see very far before you can actually express them. So a priori, they have nothing to do with adiabaticity. And all perturbations in our universe that we have measured, they are of this type. So these are actually very relevant for our universe. And primordial gravitational waves would also be of this type. So this has been a nice story to which many of the people in the audience have contributed over perhaps the past 10 years. But there is something more. So if you have a theory that is not only diff invariant but has internal symmetries, you can have generalized adiabatic modes whose definition is pretty much the same. So they are physical modes that are locally indistinguishable from a change of coordinate plus some internal symmetry. So as you can see from the definition, this is a more generic version. So you will have more solutions. So you will have more adiabatic modes in the presence of internal symmetry. Like adiabatic modes, at the classical level, they give you model-independent solutions of your equation. And at the quantum level, you can use them to prove word identities from which soft theorems follow, which is what I'm going to do in a second. So I'm going to show you the shift-symmetric adiabatic modes, meaning the one that come from having a shift symmetry. And I'm going to prove a soft theorems for this shift symmetry. So just so that you have in the back of your mind the type of theories that I'm discussing, they're P of X theory, but you can put higher and higher derivatives if you want. So our result is very generic. I don't know why I wrote the metric here. You know the metric. OK, so this theory, I claim that in principle, you can already imagine that this theory allows the symmetry of the type of the time diff that we saw before, constants over phi dot. But you can prove that only that time diff does not extend to finite momentum. Perhaps a little bit of a technicality, but if you do the analysis correctly, you need to enhance it with also some spatial diff to make it extend to finite momentum, and we did the analysis, so you don't have to worry about it. So the result of that is that we derived a symmetry transformation that I haven't written there, but is the symmetry transformation of the metric changing under this diff. So metric changes like the Lie derivative with respect to this vector. That is the symmetry of the theory. So I have a new symmetry. I can derive word identities, and here they are. Beautiful formula. I'm going to look at this formula for the case. This relates n-point functions to n plus 1 point function to n-point function, as is familiar to many of you. And let's look at it in the case of the 3-point function. The second line is Maldasena's celebrated soft theorems, and the first line is the additional corrections that we got from having this shift-symmetric adiabatic modes. In single-field slow-roll inflation, the top line is always subleading with respect to the bottom line by order q square, q long square, and so it's irrelevant. In cases like this theories, which is known as ultra-slow-roll inflation and was known to violate Maldacena consistency relation, actually the first line is leading and in fact exactly capture what was called to be a violation of the soft theorem. Actually, it violates Maldacena, but it doesn't violate ours. It's just that the other contribution becomes relevant. Time. So that's the q square. And so that's why it's subleading for the q long. I mean, there is also k, but k doesn't matter. But q is the long one. P is the power spectrum, which has a little bit of a time dependence, so it's not exactly constant. It goes to a constant, but there is a q square when you do the derivative. That's where just because zeta approaches. Very good. So this actually fixed OK, so in the last minute, I'm going to tell you about what you wanted to know. After all, we're going to try to do inflation and slow roll inflation, so we need to weakly break this theory. This is partially work in progress, so I'm happy to hear your feedback, but this is what we worked out. I'm going to show you in a second that if you plot FNL orthogonal, FNL equilateral with the current bound, that's 1 sigma, 2 sigma, 3 sigma, shift-symmetric theory can only give you stuff on this line. This is here is the argument. Let me define a model to be top-down natural if and only if it is stable. So you have a model, p of x comma phi. In my case, it would be only p of x, but the definition is for any p of x. And I'm telling you what the rule is to make it top-down natural. You should add an arbitrary function g, and the only thing you're allowed to do is to set alpha to make it very small. So you can make the coupling of your inflationary sector to Planck scale stuff. You can make it weak to control it, but you cannot control this function. This function is typically incomputable, unknown. It depends on the UV completion of gravity. For my theory, yes, but in the definition, I want it to be more general. But yes, in my theory, it's going to be only p of x. Oh, sorry, you're right. This is the theory that you have cleverly engineered that has 75 symmetries and gives you slow roll inflation and all the observable you want. And this is all the UV crap that you have no idea how to compute. So all the symmetries respected by this, for example, the shift symmetry, will not in general be respected by that. And just to quantify what I mean, this one not respecting any being generic, I mean that all of its logarithmic derivative with respect to phi and with respect to x. So all dimensionless stuff is all of order 1. We don't have good reason to believe that it's large or small. This is a technical assumption that I have to make to get some number out of this. OK, so let's compute some non-Gaussianity, everyone's favorite hobby. There is a bit of technology, but since people have extensively studied this problem, it's very easy. So there is a C3 tilde coefficient. And what we can prove is that using exactly this assumption of this being order 1, this coefficient is always of order CS squared. And so when we put it inside FNL equilateral and FNL orthogonal, this term and this term are small whenever CS is smaller than 1. So the argument is that if non-Gaussianity is large, so there is something to be measured, then CS has to be small. And so the only term that contributes are the first one. And so these two have a linear relation. When you get closer to 0, then non-Gaussianity is of order 1 or smaller, then that relation breaks down. But OK, it's going to be hard to measure it anyways. This is only for shift-symmetric theories. So the BI is not. So indeed, that's a good thing. Because so the argument is that if we measure non-Gaussianity anywhere outside here, shift-symmetric theory that are top-down natural are ruled out. Maybe they are just some approximate shift symmetry that are top-down natural are ruled out. If we measure it on this line, I haven't proven to you yet the other way around, that only shift-symmetric theory sit on this line. I have an argument, but I'm happy to give it to you in private, so I don't get too much over time. OK, so this is the summary. So we have news of theorems. We introduced the concept of generalized adiabatic modes. We show you how to fix all time dependence coefficients. And in the case of approximate shift symmetry, we have a yes or no test for the existence of a shift symmetry in the early universe. Thank you very much.